Hi guys. So today we're going to be dealing with time series in the session. Um, till now you've been doing regression, multiple regression, logistic regression, and everything. So that's for predicting a y variable given a set of x variables. There is the y variable would be different from the x variable. But in time series, what we're essentially doing is something called auto regression, which is predicting y based on its lags. So, for example, I can predict forecasts of, say, demand forecasting, right? Of sales, for example. This year's sales can be a function of the previous year's sales and the year before that, or whatever it is. It could be related. So, examples like that. Time series forecasting is quite important for, especially for demand forecasting, and it finds a lot of applications elsewhere as well. So today, what we're going to be using is a data set of tourists who've arrived in Australia from the year 1999 to 2015. So this is a built-in data set to R. It's under a package called FPP2. So, in case you don't have FPP2 on your laptop already installed, just type out install.packages and in the brackets quotes FPP2. That should install it for you. And then you can just run the command library FPP2. I'm doing that right now. Uh, I see that you guys have an issue with loading the data set, but we'll just go on for now. I'll find a fix for it and I'll post it online as to how to install the package. Yeah, so this is the Osterus dataset. You can see from the dataset that it is uh, it is a number of tourists in thousands who are arriving to Australia between the years 1999 to 2015, and there seem to be 4 quarters every year. So it's quarterly data. It's a time series by itself. But there are some data that you wouldn't necessarily be a time series at start. So there is a way to make a data into a time series, and that's using the TS command. That's I think you guys have been taught in class as well. So anyway. I mean, this is already a time series, but just for the sake of demonstration, I'm converting it to a time series. I'm using the TS statements on the Osterus dataset with a start specified from the year 1999 and quarter 1 with a frequency 4, which means I'm using quarterly data. So I'll run this. Okay, so you can see from the console here that it's essentially the same thing as the Osterus statement that's directly run, because the Osterus data in itself is a time series. And you'll find that this statement has given you the same thing here as well. So what I'll do next is I'm going to plot this time series. Okay, so have you guys been taught how to interpret a time series in class? What can you tell from the plot over here? What can you see from the plot over here? Anyone? Of course, Jared, but the other three?
It's seasonal
Okay, what makes you say it's seasonal?
because there's spikes like every year.
Yes. Okay. So that indicates seasonality. What about a trend? Do you observe a trend?
Upward.
You do observe some kind of an upward trend over here, right? Like the data is going up. So that's called a trend. And like you said, the spikes that you observe, those are called seasonalities. So this is clearly a data that has trends and seasonalities, and we're going to be dealing with trends and seasonalities using the whole Winters model later on in the session. But for now, what we will be doing is we're going to be using our normal linear regression approach and comparing it with the autocorrelation function, how they compare. So what I would like to do now is I want to predict air passengers in a year from the 4 most recent years. Uh, the statement's right over here. Sorry. Okay. So I want to predict air passengers in a year from the 4 most recent years, first separately, using simple regression. That is, I run um, using the first lag, I run using the second lag, the third, and the fourth lag independently, and then together. So the first one running separately is equivalent to running 4 simple linear regressions with different lags, and the second one running them together would imply you running a multiple linear regression using all the 4 lags at the same time. So how to find the lags of a time series? There is the lag statement. Um, so I'm using the lag statement here for the air time series object that I've created. Uh, and I'm specifying here saying it's -4, -8, -12, and -16. Any idea why that is? Yes, so each year has 4 quarters, right? So I want to predict using previous 4 years and not previous 4 quarters. If I want to predict using previous 4 quarters, then my A1, A2, A3, A4 would have lags of -1, 2, 3, and 4. But I want to predict based on the past 4 years of data. So my lags are going to be -4, -8, -12, and -16. So I'm going to run these four. It's going to store 4 different objects, A1, A2, A3, and A4 in R. Um, yeah, so now I'm going to be predicting air passengers in a year from the most 4 recent year individually using simple linear regression. So I'm just running LM commands for air against air 1, for air against air 2, air 3, and air 4 respectively. Um, we're going to be printing out the summary for this. Okay, so it says here that it's essentially a perfect fit and the summary may be unreliable. That's fine, but you can see that uh, the p-value for the air one is very small. So you can say that the first lag is significant, right? So it means that the first lag is significantly autocorrelated to whatever I'm going to predict now, right? And I'm going to be running the same thing for the second lag. It also says that it's an essentially perfect fit. The summary may be unreliable. You can ignore the warning message. You just need to know that the p-value for air2 is quite small. That means it's significantly correlated. And model 3 would show you the same thing. Model 4 would show you the same thing as well. All right. So from this, essentially, you can say that when the lags are taken one at a time and used to predict air passengers, you can say that the lags from previous 4 years of data definitely explain a lot in terms of what the future forecast is going to be like. So this is essentially the same as an ACF plot. So you guys would have been taught in class about 2 different plots. One is called the ACF plot, and the other is a PACF plot. So the ACF plot is basically running simple linear regressions on different lags taken individually. And the PACF plot is basically you running multiple linear regression on lags taken at the same time. We'll get to the PACF later, but I'm doing the ACF right now. ACF of air. So that's the ACF plot. What can you observe from the ACF plot? There is, you can see that there are blue lines above and below the zero. This means that any spike that you see over here that's above the blue line or below the blue line, it means that they are significant at a 5% significance level, right? And this means that my lag one, for example, obviously, if you notice over here from the ACF plot, you're going to see that lag 0 is going to be definitely correlated. It's going to be a perfect correlation because the data is perfectly correlated to itself, right? And The first lag you can see is well above the blue line, which means that is significantly autocorrelated. So if I take my forecast to be YT, then YT has a significant autocorrelation with YT minus 1. And YT minus 2 and YT minus 3 and YT minus 4. You can see that all these 4 over here are significant and are above the blue line, which is, can I say that it is consistent with the regression statements that I've run? The 4 regression statements that I've run for the 4 different lags? You did notice that all 4 of them were significant from the regression statement. So the ACF plot seems to agree with the simple linear regression that we ran. Now I'm going to be moving on to a multiple linear regression model. So instead of predicting air passengers from their 4 lags individually, I'm going to run them together now using one simple command, one simple multiple regression model. For that, first, what I'm doing is I'm creating a data set that binds together all the lags that I need. So I'm using the cbind statement to bind air with air1, air2, air3, and air4. So that's going to create an object that will have everything together for me. So I'll run that. Now I want to run an autoregressive 4 model. This is what they call it. So if you run a regression model and predict a y based on its lags, it's called an autoregressive model. And since we're running it on 4 lags, it's called an AR4 model. And the regression equation, obviously, you guys will be very familiar with it by now. It's given by yt equals beta naught plus beta 1 times yt minus 1. So instead of having x1, x2, x3, and x4, in a time series, you're going to have yt minus 1, yt minus 2, yt minus 3, and yt minus 4. All of them have a coefficient, and of course, there's the error term. Now I'm going to be running that multiple model. It's an lm command of air against air1, air2, air3, air4 with data equals data set, because that's the object that I created to bind all these lags together. There you go. It's a little tricky to actually understand what's going on here in the regression statement, as in like to know what those significance codes mean. So I'll tell you what it is. You can see that always remember, more the stars there are, the more significant they are. So you can see that Air 1 has 2 stars and a p-value of 0.004, which means that, okay, so from the code over here, you can actually see that 3 codes here means that it's significant at 0.001. And 2 codes here mean it's significant at 0.01, which is basically 1% significant level. 1 star row here indicates that it's significant at the 5% significant level. Just the dot over here indicates that it's significant at 10%, and nothing for 1. So you see that none of your variables, none of your lags rather, are significant at 0.1 percentage, but R1 is significant at it is significant as 1% percentage, which means that it's obviously significant at 5% as well. So if something's significant at 1%, it's definitely significant at any other levels that are above 1% as well. Needless to say. Yeah, then you have AR2, which is significant at 5%, and AR3 is significant at 10%. Now, I'm going to be running, I don't know if you guys have been taught this in class, because I went through your slides and I did not find the PACF function. So I'm going to be running something called the PACF function, which is the partial autocorrelation function. So how do you interpret the coefficients of a multiple regression model again? The slope of any variable indicates the amount by which your y increases for a unit increase in that x, keeping all others constant, which is basically the partial autocorrelation. So you're keeping everything else constant and running it on that particular X. So that means that it's partial. And that's exactly what the PACF is. I've included a definition just like a brief introduction of what the PACF function and how it is relevant to regression. So the partial autocorrelation function can be interpreted as a regression of the series against the sparse lags. It helps you come up with a possible order for the autoregressive term. The terms can be interpreted in the same way as a standard linear regression, a multiple linear regression. That is the contribution of a change in that particular lag while holding all others constant. So the PACF is very similar to the multiple regression that you run. Now I'm going to be plotting the PACF of air over here. Boom. So what do you see? And do you think it agrees with the multiple linear regression model that we just built? You can see from the PACF plot that the lag 1 is quite significant. So you need to understand one thing, that unless and until you state in your partial autocorrelation function, the blue dotted lines are going to be at the 5% significant level. So like I told you, lag 1 was significant even at the 1% significant level. So it's definitely going to be significant at the 5% level, which you can see because it's definitely significant. And we also saw here that add 2 was significant at the 0.05 level. You can see over here as well that it is significant at the 0.05 level. And you can, I also told you that this R3 is significant at 10% significance level. But unfortunately, your PSEF function, unless you specify it, it's going to be drawing your blue line for 5%. So you can see that the third lag here is quite small, and it's not significant at the 5% level. And similarly, it goes for your fourth lag as well. It's not significant at the 5% level. Any questions till now? Okay, so we'll then move to stationarity of data now. So what do you guys understand by stationarity of data? Anyone? Jared, do you want to answer?
So the time series, like the one we just saw, has a very clear seasonal trend, right? Certain parts of the year are more populous than other parts of the year. But we also see that the whole thing is moving up over time. I mean, more people are taking plane flights year to year, and in the hot seasons, they're obviously. If your data is stationary, then there's no trend moving up over time.
Yeah. So that's essentially what stationary time series is. You do not observe any trend that's moving up or down over time. And to see if a data is stationary or not, there is a very simple test that you can use. It's called the augmented Dickey-Fuller test. It can be run as adf.test and whatever your time series object is. So this is under a package called T-series. I don't know if it's installed in Jared's laptop, so I'll run it again. No.
No. But yes, it just takes longer.
Okay, so okay, there seems to be a problem again loading it.
We'll start over.
Okay, I probably need to restart R over here. I'll do that. I'll try this one more time. If it doesn't work, then I'll restart it. Okay, so I need to restart. I will.
Yes, next time.
Works. Okay, awesome. So yeah, so this T series is a package that has the augmented decufuller test. I'm going to be running the ADF test on the air data. Okay, so one thing that you need to know about the ADF test is that the null hypothesis of the ADF test is that the data is non-stationary. So whenever you observe, so when you reject a null hypothesis and like when you accept your alternate hypothesis when your p-value is less than 0.05, right? So as long as the p-value from the Dickey-Fuller test is going to give you a value of greater than 0.05, uh, you can safely say that the data is non-stationary. And you can observe here that the p-value for the air data set is 0.89, which is a lot, which means that the null hypothesis is quite strong and you can't reject it. And therefore, the data is clearly non-stationary. You guys wouldn't have been taught this in class, but I would just like you guys to know that differencing techniques are generally used to make a non-stationary time series stationary. So it's just a command again. It's called diff that can be run on the time series. So um, what this essentially is going to do, I'll run. Okay, so it's going to take the difference between. I'll just show you the difference. Okay. Yeah. So you can see that what this diff command has done here. Quarter one of 1999 does not have any previous data before that, so there's nothing to differ it from. But quarter two of 1999 is subtracted from quarter one of 1999, and that gives you a minus 10.9 value over here. And similarly, 25.31 minus 19 gives you 6.16, and 27 minus 25 gives you 2.27, and so on. So what this differencing does is it basically differences your next data with the previous data. And I'm going to now run the ADF test on the diff of air and not the air. You can see now that from the augmented decufuller test, the p-value has gone below 0.05. So, and I can actually plot this for you guys and show you that diff of air is not going to have any trend. Do you observe any trend over here? Do you observe an upward or a lower trend? I know there are seasonalities, but you can see that the trend has been eliminated. You don't observe an upward or a lower trend. So that's basically what differencing does. And generally, when your time series has like crazy trends, you might need to difference it more than once to make it to make it stationary. So you would just keep on differencing it till the ADF test gives you a p-value of less than 0.05. And keep differencing it in the sense that you just put ADF test of diff of air, or diff of air. So that's going to work for you. Perfect. Okay, so any questions on this, the ADF test, or on stationarity of data? Okay, we'll move on to the next. Now I'm going to be fitting a linear trend. So we can predict a linear trend by predicting y from time. but in your data set here, you don't have a variable that has time in it. Uh, we we don't have, like I said, a variable that has time in it, but we have a year and a quarter variable instead. And we can actually get a variable in R that represents time by just using the command time of x, whatever that x is. X would be that object. So here, in my case, it would be time of air. And using that, I can fit a regular regression. And that model I'm going to be writing now. So model 2 is an LM statement of air against time of air. Summary. Okay, so how do you interpret the results of this model? Remember that when you put the time statement over here, it's going to be calculating in years and not in quarters. So a unit increase in your x variable, that's the time of air, would mean an increase in a year and not a quarter. So it's just the regular regression, so you know how to interpret the coefficients as well. Okay, so this is just another demo, and we'll actually move on to exponential smoothing now. Um, so exponential smoothing is one of the modeling techniques for a time series, and um, you guys would have been taught the simple exponential smoothing model and the Holt-Winters model in class. So I'll be demonstrating those in R for you now. So an exponential smoothing model can be called from the forecast library. I hope I ran okay, and yeah, I'm just naming it as SES because SES is simple exponential smoothing. That's the command. So air.ses is a simple exponential smoothing of air given an alpha of 0.5. So if you do not mention the so alpha is one of the parameters in exponential smoothing, right? So if you do not mention the alpha value inside your SES statement, it's going to take the optimal alpha value, which could be good in some cases, but I'm anyway using the alpha value now for demonstration purposes. Perfect. Okay, so how does it optimize the alpha value? So any prediction that you do, you can call it optimal if it minimizes the errors, right? So it will select the optimal alpha by minimizing the prediction error on your data. So that's how it does it. Um, instead of a simple exponential smoothing, and you will see when I show you the plot of the simple exponential smoothing. What do you observe from this? So till 2015, I have the actual data, and beyond that, it has actually forecast. Uh, do you think the forecast is good? Not at all, right? I mean, there seems to be a lot of spike before 2015, and it's just a flat line after 2015, which means that it's actually predicting it quite badly. It's not precise at all. And also, it's the case that if you see the confidence interval cone over here, so this corresponds to the 85% if I'm right, and this corresponds to the 95% confidence intervals. You can see that the intervals are quite wide, which is not really good when you're like running forecasts for a company or some sort of something like that, because wider your confidence intervals, the more unpredictability in knowing what your actual forecast could be. So you would want your forecast interval to be as small as possible. That is, I'm talking about the difference over here. Can you see this over here and over here? So you want that to be as narrow as possible. And you obviously, for very clear reasons, this is not really a good model to for our data set. And now I'm going to run a Holt model. A Holt model is basically one that takes trends into account, but not the seasonalities. So I'm going to be running that. Okay, I'll plot the Holt model now using the plot command. again, you can see that it's improved a little bit from your simple exponential smoothing model. But it's still bad because again, it's a flat line. It hasn't taken into account the seasonality in the data that you've been given. So the Holt model is again not really a good forecasting model for this data. But you can and you will observe that the Holt Winters model, which takes into account your seasonalities as well. So every time, so the thing about all these models is that they get increasingly complex as well. And sometimes, and this is very true for the case of ARIMA models, people generally prefer a more parsimonious model that involves predicting a lot, it involves calculation of a lot less parameters than you want to. Uh, so in that case, some people prefer using simpler models, but you can see that this model is actually not performing that well. So you definitely need an extra parameter to be predicted, and that is your gamma that you're giving to the Holt Winters model. So I run the Holt Winters model now, um, and I plot Holt Winters. There you go. So is that much better than whatever we've observed with the simple exponential smoothing and the Holt model? You can see that the confidence interval is also quite narrow, which means this obviously the spike indicates that it's consistent with the previous year's data, and also you can see that the confidence interval you literally can't see the cone over here. It's quite good. So the whole winter model is probably the best model in predicting the forecast for this data. Any questions?
I believe in class we'll be going over time series again on Monday and Tuesday, right?
Any questions? Concerns? I guess some of this will help you with the homework as well, for the most part.
I have lots of next week's homework, so.
Yeah, so yeah, it's going to be good. If there are no other questions, I think we'll wrap up. Thank you, guys.